Hi everyone, welcome to the first lesson. My name is Ezra and I'll be covering the fundamentals of blockchain to give you a broad perspective of this rapidly evolving technology. So first, let's begin by understanding what it means to be decentralized. I'll be using a payment system to illustrate what it means to be decentralized. Let's say that I would like to transfer some money to Gary. I could use various transfer methods such as PayNow, PayLah, or do a wire transfer. However, regardless of the transfer method, the transaction still needs to go through the bank. The bank essentially is the central intermediary or middleman between Gary and myself. I rely on the bank to ensure that my money reaches Gary successfully. In other words, my trust is dependent on the bank. There is a central authority that needs to approve, verify, and authorize the transaction. However, what if I'm able to transfer money to Gary on a decentralized payment system? If this is the case, then I would not need a bank to act as a middleman to make a transfer to Gary. I can communicate directly with Gary and make a transfer without a middleman, such as a bank, to decide whether my transaction will be successful. The key takeaway from this example is that operating on decentralized systems does not require a middleman. This applies to many other types of applications which I will go through during the later part of my presentation. So next, I'll be covering the architectural software of centralized and decentralized systems. In centralized software systems, the components are located around and connected with one central component. In contrast, the components of distributed systems form a network of connected components without having any central element of coordination or control. So as you can see, there are two figures that depicts both architectures. The circles in a figure represent system components, also called nodes, and the lines represent connections between them. At this point, it's not important to know the details of what these components do and what information is exchanged between the nodes. The important point is the existence of these two different ways of organizing software systems. Figure A shows a distributed architecture where components are connected with one another without having a central element. It is important to see that none of the components are directly connected with all other components. However, all components are connected with one another, at least indirectly. Figure B on the right illustrates a centralized architecture, where each component is connected to one central component. The components are not connected with one another directly. They only have one direct connection to the central component. So briefly going through the pros and cons of distributed systems. The main advantages of a distributed system over a single computer are its high computing power, cost reduction, high reliability, and ability to grow naturally. And its main disadvantages are its coordination overhead, communication overhead, the dependency on networks, and higher program complexity and security issues. I'll go through more in detail during the lesson itself, but for now, just take note of the disadvantages and advantages of decentralized systems. So now that we understand the difference between centralized and decentralized systems, it is important to note the existence of mixed systems that contains elements of centralization and decentralization. The diagram on the left-hand side, figure C, illustrates an architecture that establishes a central component within a distributed system. On first glance, the components seem to form a distributed system. However, all of the circles are connected with the larger circle located in the middle. Hence, such a system only appears to be distributed on a superficial view, but it is a centralized system in reality. The diagram on the right-hand side, figure D, illustrates the opposite approach. Such a system appears to be centralized on first glance because all the circles in the periphery only have one direct connection to a large central component. However, the central component contains a distributed system inside. The components in the periphery may not even be aware of the distributed system that lives within the central component. What these two approaches have in common is that it is hard to determine their true nature. Are they distributed or are they centralized? At this point of time, it is not necessary to give these architectures unique names. However, just take note of their dual nature. This is particularly important because it may not be easy to spot the centrality or the distributed nature within them. So the emergence of hybrid architectures makes it hard to identify distributed systems clearly. However, for this lesson, it is important to have an idea of what a distributed system is and how it differs from other software systems. If you're in doubt whether or not a system is distributed, look for a single component. For example, is there a login or logout component? Is there an emergency switch off button that could terminate the whole system? If you find such a component, the system under consideration is not distributed. So, for example, your laptop and your handphone will be considered as centralized systems. So now we're talking about distributed ledger technology. This is important because I'll be covering how cryptocurrencies operate on decentralized systems such as DLT in the later part of the presentation. So the main purpose of the blockchain is to achieve integrity in distributed software systems, which is a non-functional aspect of the implementation layer. And blockchain has a feature called immutability, which essentially means unchangeability. Immutability is one of the key features of Bitcoin and blockchain technology. Immutable transactions makes it impossible for any entity, for example, a government or corporation, to manipulate, replace, or falsify data stored on the network. This means that once a block is added to the main chain, it cannot be altered or removed. It is considered to be part of history. So now we're covering the components of a block. As you can see, in each block, there is a header and a body. The header contains the hash of the previous block, timestamp, nonce, and marker root. The body contains the transaction data. Now, what do I mean by the hash of the previous block? It means that each block contains data of the previous block. For instance, the hash data of block 1 takes reference from data of block 0. If I change the data in block 0, this will also completely change the data in block 1. This feature of the blockchain is important to explain why it is very difficult to hack a blockchain, which will be covered in future lessons. Now, the next important thing to take note is the marker root. And this is created by repeatedly hashing together pairs of transactions, which eventually gives you a final root hash that is the unique fingerprint of all transactions in a block. So for instance, transaction 1 has a hash of hash 1 and transaction 0 has a hash of hash 0. Combining it will give you hash 0, 1. This works in a similar way for hash 2, 3. If you combine hash 0, 1 and hash 2, 3, we get the root hash of the marker root. It is very easy to identify if the data has been tampered with. If let's say someone changed the data of transaction 1, the hash 1 will be different, causing the final root hash of the marker root to be different as well. So one of the functional requirements define what the system does or must not do. Non-functional aspects of the system specify how the system should do it. Non-functional requirements do not affect the basic functionality of the system. So for instance, functional aspects are things like, for a payment system, they have features like depositing money, withdrawing money, transferring money, and monitoring your account balance. And the non-functional aspects are also important to protect the system in various ways, right? So such as ensuring a privacy, it is fraud resistant, and the ability for you to use it 24 hours a day are examples of non-functional aspects. So here's a summary of blockchain. So moving on, I'll be covering peer-to-peer systems. A peer-to-peer system is a distributed software system consisting of individual nodes. Participants and users are able to turn their individual computers into nodes. So, the definition of a peer-to-peer system is that it is a distributed software system that consists of nodes or individual computers which make their computational resources, for instance, their processing power, storage capacity, or information distribution directly available to one another, right? And how are peer-to-peer systems changing the world? So for this example, I will use the music industry. In the past, when musicians wanted to produce and sell music, they would need to hire the expertise of a studio. These studios acted as intermediaries between the musicians and the people due to their exclusive knowledge and skills in producing, marketing, and distributing music. More often than not, these services are expensive, which cut the profit margins of musicians and increase the cost of music for consumers. However, a company called Napster played a major role in the replacement of music studios as intermediaries. It allowed people to share their music files directly with each other without having the need to purchase CDs. The peer-to-peer system created by Napster formed a digital sharing bazaar for MP3 files, which gave consumers a wider range of music. This ultimately disrupted the music industry, causing significant losses to the music studios. So essentially, Napster provides a central directory for the music files that are available on the network. It is important to note that no music files are stored in the central index. The purpose of a central index is simply to inform users of the music files available and connect them directly to peers that have the music files on the internet. So this is how this is a diagram showing how Napster works. So the Napster case has shown us the potential of peer-to-peer systems disrupting industries that as a middleman between producers and consumers. Other industries that could potentially be disrupted by such technologies include banking and real estate. In peer-to-peer systems, transfers will be much simpler and takes less time and cost due to the similar nature of two peers and nodes that transfers data in bits and bytes. So the main advantage of a peer-to-peer system, as mentioned, is the less processing time and lower costs. So now that we have a good understanding of the potential of peer-to-peer systems, I'll be briefly going through the architecture of peer-to-peer systems. In general, peer-to-peer systems are distributed computer systems by construction since they are made of individual nodes that share computation resources. However, peer-to-peer systems may also utilize elements of centralization. One such example is Napster, which provides a central directory for users to search up files, products, and services offered to the network. So while peer-to-peer systems are amazing, it is also important to maintain trust and integrity on a network. Peer-to-peer systems make use of blockchain to achieve the integrity needed so that users will continue to have a pleasant experience using the system in a fair manner. The two main reasons why a blockchain is needed is firstly, technical failures. Technology is always prone to fail. Hence, the system needs to have the ability to continue normal operations when individual components fail. Blockchain helps to solve this issue due to its distributed nature. The second reason is malicious peers who act dishonestly. Malicious peers pose the greatest threat to peer-to-peer systems as they attack the foundation which the peer-to-peer system was built on. Blockchain systems helps to solve this problem, which will be explained later. Now, as explained, peer-to-peer systems leverage on blockchain technology to achieve and maintain integrity. Peer-to-peer systems are constantly improving and have the potential to disrupt many industries. So I'll briefly go through the differences between public blockchain, private blockchain, and permission blockchain. In a public blockchain, anyone is free to join and participate in the core activities of the blockchain network. Anyone can read, write, and audit the ongoing activities on a public blockchain network, which helps the public blockchain maintain its self-governed nature. Compared to a private blockchain, for a private blockchain, if one needs to run a private blockchain that allows only selected entry of verified participants, like those for a private business, one can opt for a private blockchain implementation. A participant can join such a private network only through an authentic and verified invitation. A validation is also necessary either by the network operators or by a clearly defined set protocol implemented by the network. For permission blockchains, usually they contain a mixture of both public and private blockchain properties. So next, I'll be covering the fundamentals of cryptocurrencies. So what does it mean to have a cryptocurrency? Does it mean that a currency that is digital, a currency which the government does not control, magic internet means, or even something that uses cryptography? Well, just imagine that you are in a group, you have a small group of friends, and you consist of 4 merchants who frequently do business with one another. Now, it is super inconvenient to exchange money all the time, and we do not want to hire someone to manage our money. We want to do all of our transactions internally. So here's an idea. Why don't we keep a common ledger to record all of our transactions? So if I'm going to transfer some money to Gary, I'll record on the common ledger that I'm paying Gary $100 so that everybody knows that I'm paying Gary $100. And the rules of the protocol are that this ledger is publicly viewable, right? So if anyone makes a transaction, we add a line that states the sender, receiver, amount paid, timestamp. At the end of a period, we sum everything up and set up in cash. So all the transactions on the common ledger can be seen by everyone. So if I pay Gary $100, Justin and Josh will also know that I had paid Gary $100. However, we have a slight problem. If anyone can just add transactions to this ledger, people can just come in and insert false transactions. It is problematic if someone can add lines without someone's approval that the transactions indeed happened. So the solution to this, to overcome this problem, would be to use digital signatures. A digital signature helps provide proof that whoever is the sender of the transaction has seen it and approved it. In other words, you can only add transactions where you are the sender. It must be invisible for anyone to forge this signature. Digital signatures are actually just a bunch of 0, 1 bits. But it seems like intuitively anyone can just copy this. So to solve this problem with the public-private key pair, which I'll explain soon. So moving on, I'll be covering digital signatures and cryptography in detail. So just imagine that you would like to send a letter to your friend. You know his residential address and mail him the letter. The postman inserts the letter into your friend's mailbox. Now, only your friend can open the mailbox because he owns the letterbox key required. This letterbox key is unique and only he has access to it. So this letterbox example illustrates the use of a public-private key pairing. Your friend's residential address is the public key which you need to ensure you send the letter to his address correctly. And the letterbox key, which only your friend has, represents the private key, which only your friend can open because he's the sole owner of the private key. So the goal is with digital signatures, is to identify owners and property uniquely, and to ensure that only the lawful owner can access his or her property. And the main challenge of this is that for the blockchain is to protect the property assigned to the accounts without restricting the open architecture of the distributed system. So like as mentioned, the idea is to treat accounts like mailboxes. Everyone can transfer property to it, but only the owner of the account can access the things that are collected inside. The major characteristic of a blockchain is that its location is known, and hence anyone can put something in, but only the owner can open it with a key. So blockchain uses asymmetric cryptography. Asymmetric cryptography consists of 2 complementary keys. For example, you have a message that reads "Hello World." If you use a black key to encrypt the message, you will get a ciphertext. The message can only be decrypted with a corresponding complementary key. In this case, it is the white key. The important thing to note is that the key you use to encrypt a message cannot be used to decrypt the same message. You can switch the roles of the keys as you like for every new piece of data you want to encrypt. But you always have to keep both keys for doing both encryption. If you have only one of the keys, your power is limited. On the right-hand side, a white key was used to encrypt the message, whereas the black key is needed to decrypt the message, but the output message is the same. So moving on to public key and private key cryptography. The public key is visible to all, and the private key is kept secret. It should be completely invisible to generate a signature if you don't have the private key. While someone may attempt to forge his signature, depending on the length of the security, it will require a lot of work. Now remember that the signature completely changes if the content of the message changes, just even slightly. To prevent copies, make sure that each entry has a unique index number. So we will add a new rule to our ledger and protocol, which is we will only accept valid and signed transactions. However, we have a new problem. How can we trust that everyone will follow the rules of our ledger? People must be trusted to settle and pay up. People should not be allowed to spend unlimited amounts of money. So our requirement is that we don't allow overspending. Everyone puts a certain X amount of money into the pot. No one can spend more than what they own. This will require our ledger to always have the full history of transactions. Protocol to reject transactions that causes someone's balance to go negative as invalid. So this is all very important to prevent overspending. So with trust issues, we will have a very big problem of deciding who has control over the place of where this ledger is hosted or stored. Now remember, we don't trust any third parties involved, and we can't have someone internally managing it for conflicts of interest. The solution to this problem is to have a decentralized ledger, and everyone owns a copy of the ledger. When anyone wants to execute a transaction, they will broadcast. For instance, they will inform everyone of a transaction being added. But we still have a new problem, right? How can we be sure that what is broadcasted is valid? And how can we trust that other people receive the same message? Now, this is a very common problem in the military. It is called the Byzantine generals problem. And we use this to talk about blockchain as well. So just imagine you are a general of an army for the Byzantine Empire. There are several other armies all camped around an enemy city, and you're all deciding when to attack. If you all attack together, you'll be successful. If you all retreat together, you will successfully retreat. If only some of you retreat, then you will fail and suffer huge casualties. Now, the problem lies in how the generals communicate. Each army uses the same messenger to communicate with each other. The only way for the messenger to move between armies is to sneak through the enemy city. This makes the messenger untrustworthy, as there is no way of ensuring that the message you receive is true and correct. The messenger could be captured, a general could be a traitor, or you could receive no message at all. Just imagine I send a message to the other generals, let's attack Monday at 11 a.m. And the other general responds, well, let's attack Tuesday 11 a.m. As you can see, the message is tempered with along the way, and the message I received says, agreed, let's attack Monday 11 a.m. I now incorrectly believe that we have reached consensus. This agreement results in catastrophic casualties and failure. So, how can we trust strangers on the network? Well, we need a protocol to accept and reject transactions in a certain order, such that everyone will be enforced to follow the same ledger. We will trust whichever ledger has the most computational work put into enforcing this ledger, and the computational work involves a complicated mathematical puzzle. The requirements for this puzzle is that it must be extremely hard to solve, but very easy to verify the correct solution. For instance, Bitcoin uses a cryptographic hash function as its mathematical puzzle, right? And it has to operate on a trustless system, which requires no middleman or third party. So now I'll be moving on to discuss consensus mechanisms, right? So what are consensus mechanisms? Whenever there is a debate of which data is true or which data is false, we need to achieve group consensus. So we try to achieve group agreement on data values or the state of network among distributed nodes. To solve the Byzantine general's problem in distributed systems by allowing nodes to agree on only one state. And there are multiple consensus mechanisms such as proof of work, proof of stake, proof of authority, and proof of burden, and many more, right? I highly encourage you to search up more types of consensus mechanisms and get a brief understanding of how they operate. So, what are consensus mechanism principles? So there must be a way to align interests and incentives for the players in a distributed setting. So validators provide something that they will lose if they acted dishonestly, but there are also rewards for those that choose to act honestly. There must be an easy way to check anyone playing cheat and an easy way to validate the truthiness of a ledger. The system should also try to be egalitarian, inclusive, and participatory. So proof of work is the original consensus algorithm in the blockchain network. This responsibility bears on special nodes called miners and a process called mining. The main working principles are a complicated mathematical puzzle and the possibility to easily prove the solution. I believe in the second lesson, we will go through in detail of proof of work, but for now, this is just a brief definition of proof of work. So, yeah, we always follow the longest chain. So in proof of work, there are times where we reach a crossroads where there might be more than one, the chain splits up into two different pathways. Just take note that for proof of work, we always follow the longest chain because this implies that most computational work has been performed on that main chain. So we always follow the longest chain. So proof of stake is a little bit, actually a lot different from proof of work. We call them validators instead of miners. Validators don't need to use significant amounts of computational power because they are selected at random and aren't competing with each other. They do not need to mine blocks. They just need to create blocks when chosen and validate those blocks when they are not. This validation process is known as attesting. The main idea is that participants can lock or essentially stake their coins at particular intervals, and the protocol randomly assigns the right to one of them to validate the next block. If you attest to malicious blocks, you lose your stake. So this is the main differences between proof of work and proof of stake. So just briefly, I'll be covering the last part of my presentation, which is the blockchain trilemma. So the blockchain trilemma, essentially, it is a concept coined by Vitalik Buterin, the creator of Ethereum, and he proposed a set of three main issues that developers encounter when building blockchains. More often than not, creators are forced to sacrifice one aspect for the sake of the other two. Right? So essentially, for the development of blockchain, we usually take three aspects into account: the decentralization, the scalability, and the security of the system. But the big problem that most developers face is that whenever they try to scale their project and upgrade their project, they can usually get two of these aspects to be upgraded, but there's always one that lags behind. So this is the challenge that most developers, if not all of them, will be faced with when they try to advance their blockchain applications. So in detail, we will discuss more about this in class, but for now, just take note that this is a problem that exists in the blockchain world. So I know it's a long presentation, but thank you for listening. And if you have any questions, you can ask me during class, and I'll see you in class. Yeah, thank you very much.